Okay, so the next part of this talk is um, just having an overview of performance and kind of what Forge provides in terms of profiling. But a good place to start before kind of you delve into the tools is to kind of look at this performance roadmap, as I like to call it, because this, I think a lot of performance is around a specific methodology that you use. If you have a good methodology, it kind of helps you to focus on how you get the best performance of the application. So we kind of look at this road and kind of like you think of performance as you're going down a performance route. So if you start on the left-hand side, which is around bugs, this is usually the the stage which contributes to quite a lot of performance issues. So, for example, if you have bugs in your code and you're running this for quite a long time, and then all of a sudden your application just crashes, and that's kind of not very good because what you've done is you've potentially wasted some resources on the system. So kind of you want to make sure that all the bugs are fine and they're right, you get the correct answer out of everything before you start looking at particular performance and optimizing it. So yeah, as you go up this route as well, so IO is the next big thing. Because if you get IO wrong, you could really impact the performance of your application. But not just that, if you have a shared file system and you're using that file system very inefficiently, then potentially you're impacting everyone else who's using that shared file system as well. So an example of this is if you have an application that's very IO heavy and it's busy writing to the file system as it's busy running. So you run your application, it's just doing lots of these writes to it. Now that's going to impact your application. And what you might do instead is at the start of your run, you could as part of the setup, you could collect everything that you want to write and read that all in the beginning, run the application at the end of it, then do one write to the file system. And that's more efficient use, for example. Yeah, so as you go up this, then there's workloads, and the workloads could be things like imbalance. There could be a range of MPI ranks, which is doing a lot of work, and there could be a few that finishes early and is sat there at a MPI barrier, for example, and just not utilizing all the ranks as efficiently as possible and causing that imbalance could affect the performance of the application. And then moving on a little bit further, if you solve that problem, you can look at communication. So things like message sizes, as well as some of the communication overheads as well. So particularly if you have quite a lot of OpenMP threads, and if you're using too much, then it might not actually be that efficient in running your application because all of that time might be spent in just overheads instead of it could be using somewhere else. So yeah, so you workloads, communication, then you can look at your memory, and you can look at cores, and then towards the end of it, you can look at vectorization. And it might just be that your code isn't set up in a specific way to make use of vectorization. So you might need to restructure some of your code for that. But once you've done each of these stages, so if, for example, you do IO, what you need to do is you need to verify your code again. So you'd use a debugger to make sure you still get the right answers and that your code is still running as expected. So it's part of like verifying it after you've made some changes. So what Linaro provides is performance reports, and this gives a kind of high-level overview of the performance. And this is kind of nice in the fact where you can kind of build a culture of application performance and efficiency awareness. So if you just run your application and you come back with an answer, then you might not know what's going on with the performance of your application. But if you run something like performance reports on top of that, you can look at performance and then you can do something about it. So an example of this is if you run your application and then this performance report is available to you, and then you can make some decisions based on this, on where you want to focus some improvements. So for example, this specific application is running and then 20.6% of the time is being spent in compute. So this performance reports give some metadata. So in the metadata, it tells you how many nodes you're running on, what command you use to run it, how many open npnum threads you're busy using, and how long the wall clock time of the run was. So for this specific example, it ran for 3 minutes. And out of that 3 minutes, 20.6% of the time is spent in compute, 63.2% of that time is being spent in MPI, and 16.2% of the time is being spent doing IO type operations. And the nice thing here with performance reports as well is it gives you some hints and tips about if your performance looks good or where you should be focusing your attention. So in the 3 minutes, performance report is saying that the time spent in compute is very low, so you should be focusing on either MPI or IO performance first. And then it's saying, sorry. And then it's saying for the MPI, this is quite high. You kind of want to look at your MPI breakdown, and what you want to do is you want to find some advice on how you can reduce that. And then finally, your IO is quite average, but this might be something to look at. And this is where it relates back to that performance roadmap as well. So in the roadmap, it says, well, IO is a little bit more important to look at. So that's actually where we'd want to focus the time. So even though the MPI is quite high, you really want to focus more on the IO and making sure that's okay before moving on to that. So that's the high level overview, and then performance reports gives a more of a breakdown. So even though 16.2% of the time is being spent in IO, we can see the time spent in reads is 0%, and all that time is being spent in write, so just writing to the file system. And the effective process write rate is 1.38 megabytes per second, and performance report is saying that this may be caused by contention for the file system. And really want to find like an IO profiler to have a look if this can be improved. And once you fix all the IO issues, and it might take a bit of time, then the next step will be look at some of the MPI issues. But there is further breakdown as well. So not just IO, you can look at things like the CPU time, and you can look at single core code. And what that says is how much time is being spent just doing single core operations, so nothing that's being parallelized. You can look at your OpenMP regions as well, MPI, IO, memory, and some energy things as well. And each one of these breakdowns, performance reports is giving us some hints and tips. So for example, on the OpenMP, we're saying 58.9% is being spent in computation, and the physical core utilization is 100%, which seems quite good, but there is quite a lot of synchronization occurring in some of these parallel regions. And so what you want to do is you want to put a profiler on that and look at where these synchronizations are busy coming from. And likewise, in the energy part of this, performance report is saying that a significant time is being spent waiting for memory accesses. And so you might want to look at some of the memory accesses to reduce some of the energy, for example. So that's all well and good if you have a roadmap, you run your application, and from that performance report is telling you what you should be looking at. But then the next step past that is how do you actually make a performance improvement. It's very well and good that the profiler is saying that there's a bottleneck or there's an issue, but you still have to work at how you can fix it. It kind of like what I like to think about it is kind of thinking, coding, and then running. So once you know that you have a potential performance problem, it's kind of thinking about why that might be occurring, and finding some options around there, and then do a bit of coding to fix that issue, and then doing some experiments as well around that. So continuously running with different options and seeing which option kind of works best. So if we look at this particular example, so this is looking at matrix multiplication. And what would happen is that each processor would read and write main memory in contiguous blocks. And any previously accessed cache lines are stored within the cache. And the cache will sit near the processor. So as these calculations are occurring, if you're making efficient use of the cache, then all the calculations will continue to grab these things out of the cache, and this makes it more performant. But if you have poor spatial locality, that means that the information might not necessarily be in the cache. And so what will happen is that the process has to go all the way to main memory to grab that information. It might have to go to the L2 cache, it might have to go to the L3 cache, but if it's really bad, it might have to go out to main memory all the time. And all this slows things quite significantly. And what you could do is you could change some of these for loops around to make better use of the cache and making the application run a little bit more efficiently. And you can do some experiments around this. You can change the values of these for loops. So for I, for j, for k, for example, the time this runs could be quite high, but then if you run it with JKI, you can see it's even worse. But then you can find the right kind of balance of performance for example, IKJ, and this seems to make the best use of the cache. But it's kind of thinking about that. It's how does this cache work, and why would something be inefficient, and then trying things around that and coming up with the best solution for that. And Linaro Map does provide some features that kind of helps with these kind of experimentations, so to say. So one of the features is you can find the peak memory usage. So as your application is busy running, it samples all of the memory usage over time, and you can see where this peaks up. And from that, you could probably just use something like a debugger to see why is it going up, and having a look at the code which is causing some of those memory spikes. You can also look at imbalances with map. So if there's some processes that's on an MPI barrier, and that's quite, the time spent in the barrier is quite high, that usually means that some of the other ranks might just be taking a bit longer, and so some of those processes has to be waiting for those to finish. So that's a good indication that there could be imbalance in your application. And you can also look at things like OpenMP regions, and you can zoom into a specific region, and you can see if there's high synchronization there, which is usually denoted by this gray coding, or the gray coloring in that area. And if it's high synchronization, you might think, well, why is it such high synchronization? Is there anything I can do to reduce that? Yep, and finally, there could be some restructuring for vectorization. If you have this calculation, you can see there's no vectorization occurring on this particular line. You might change some of that code and restructure it so that you can make better use of vectorization. So just going a little bit deeper into map. So map is a source level sampling based profiler, and what this means is that you don't need to instrument any of the code as you run the application. Normally, you just append map minus minus profile to it, and it will start collecting some samples. Yeah, and it's really designed for hotspot analysis. So as you run the application, you can see that there's some hotspots in particular areas, and those hotspots are the areas that you'd want to focus on. So just looking at this visualization, what you can see is there's an application activity, and what the application activity is saying is what the processes are doing over time. So on the x-axis is time, and on the y-axis is how many processes are doing a specific operation. So you can see, and all the operations are color-coded. So blue is MPI, dark green is open. Yeah, just so dark green is the main thread compute, orange is IO, and light green is open MP type operations. So in the application activity, you can see for the first few seconds, there's some processes that are doing main thread compute, some threads that are doing IO. I think the gray is sleeping, so some processes are sleeping. It's running with 32 processes, and yeah. And then you can see after that initialization phase, what happens is the application activity starts changing, and there's a bunch of MPI that's occurring and OpenMP type operations for most of the time that the profile ran. And then at the end of it, it's doing probably a cleanup of the application, kind of the exiting of the code, which is again doing some main thread compute, some IO, and sleeping. And so from the application activity underneath that, you have something like the CPU floating point operations, and there's a range of different parameters that get included as part of this. But that gives the distribution of the metric value across processes, and there's a range of things you can do. CPU instructions, you can do IO, you can do things like MPI. And again, this relates to the application activity. So again, on the x-axis is time, and the y-axis is the distribution of that value across the processes. So you can see how that relates to the application activity. And again, there's something like memory usage you can look at as well, and you can see how the memory usage is being distributed over the running of your application, which again relates to your application activity. And you can also do things like Linux perf events, so cycles per instruction, CPU cycles, the L2 cache accesses, and you can see how different metric values are relating to the application activity. And all of this should help to kind of drill down into what an issue might be. So map also only collects 1,000 samples per processor, and it throws the rest away. Oh, sorry, yeah, there's a question. Hi.
Yeah, so is there a way to put these numbers in some type of context? Like is there like a good cache miss rate that one should be trying to achieve, or like what's the peak compute power of the given CPU that, like how much percentage you're achieving? Like how do you go about determining that you're not doing well enough?
Yeah, so there are some things in the documentation which kind of gives you the expected things which you'd want to see. So, for example, you want to see low cache misses as an example, and there's a couple of other things around CPU floating point. You want that to be kind of as high as possible, and your memory usage you want to be quite low. But all of this is in the user guide, and as part of the hands-on, I kind of go through the these values and what the user guide says are good values or not so good values, or what you would expect.
Okay, Thank you.
Yeah, but then again, a lot of this as well is kind of like some things if you're doing performance engineering, which is not that obvious as well. But yeah. So yeah, so the map throws away, only keeps 1,000 samples per processor, and the rest it throws away. It is based on this adaptive sampling rate. And all what this means is that it keeps everything low overhead. It doesn't really matter if you're running on thousands of processors or if you're running this for a very long time, it will keep the map file quite small. So we talk about ranges of megabytes instead of gigabytes, but you'll still get quite a lot of the information that you need. It's not like you're losing any information. And this GPU profiling, unfortunately, I put the wrong screenshot on here. So this is actually a AMD profile instead of a NVIDIA one, but it's exactly the same with the profiling, which you'd see is in the main thread activity. Yeah, you have mixed CPU, which is in green, as well as GPU, which is purple. And this the purple really is the CPU time waiting for the GPU kernels. So if you think, well, you're in host code, but the GPU kernels are still busy running, the purple will be how long it's waiting for those kernels to finish before it comes back to the host code. And then we also have this GPU kernels graph, which indicates the kernel activity. So you can see that there's a couple of kernels running then how much time is being spent in each one of those kernels. As I said, the same year is for NVIDIA GPUs as well. The only difference is CUDA versus HIP. But you can also get a breakdown of different things like the GPU utilization as well as GPU memory utilization. You can see what happens is for the first few seconds that there's no GPU utilization, and then towards the middle of your application run, that starts spiking up. And there's a bit of a pattern there as well. And then towards the end, when it starts doing MPI, your GPU utilization goes down again. The map also supports Python profiling. Yeah, so if you want to profile your Python application, you do map -- profile, your srun command, and you just type Python and the name of your Python application. So pretty much it's just running your Python application as you would normally, but you append map -- profile to it, and then you should be able to get a profile. And in this pink, the color pink denotes the amount of time that's being spent in the Python interpreter. So this particular application, there's some blue, which is your MPI, and then your pink, which is some Python code as well. And again, you can have a look at all these different metrics and how they relate to the main thread activity. So this particular application as well it's a mixed code, it's a mixed language. So you can see some of the C routines being profiled alongside the Python code. Yeah, so map also gives a percentage. So in each one of these main thread stacks, it kind of puts the highest or where most of the time is being spent on top, and it goes down and orders them all the way down to where the least amount of time is being spent. And typically you can display this in two ways. You can just display this as a percentage. So you can say this application ran for, say, 20 minutes. And now those 20 minutes, 20% is being spent on this line, 20% spent on another line, for example. Or you can change this to core time. And what this says is how much time is being spent, kind of if you ran that part of code in serial. So in this particular example, it ran 16 cores for say 1 minute, but on slow F19 line 114, it ran for 2.8 minutes on that line. But that's a core time minutes. Is, as I said, if you run that kind of in series, that's how much time would be spent there. And that's kind of like what you could do is you can make a performance improvement and then see how much actual time you're saving rather than a percentage which might not be as useful in some cases. And you can toggle this, there's a little clock on top of map, and you can toggle that between percentages and core time. So libraries in map as well, you can click on the libraries tab, and what this does is it lists all the time that are spent in different libraries. This is a good way to see or to change out libraries. So for example, if you're using the BLAST library, for example, versus your own maths library, and you can see which is more efficient. And then just swapping out libraries to see if it helps with some of the time being spent there. Hardware performance metrics. So this is map uses the perf or PAPI to gather the data. And you can get some information on some of the hardware counters. So things like the cache misses or cycles per instructions. So those type of things. But we are kind of looking more towards the derived metrics. So this is not implemented yet, but what derived metrics would give, hopefully, will be to do some calculations on these values to give kind of like more of a top-down methodology to performance. Yeah, so I mean, with the derived metrics, you'll be able to calculate things like flops per second, and you'll be able to kind of say what's the L2 cache accesses divided by the L2 cache misses, and this might give you some further information on performance. Okay. The last thing I want to cover is Thread Affinity Advisor. So this is built into MAP. And actually, like one of the questions is, well, why should anyone care about affinity? And the answer to that is really, if your affinity is quite bad, it can silently degrade the performance of your application. And really, you can't see much of if affinity is causing a problem without good tooling. So things that it could affect is if you have resource balancing, for example. So you might be sharing some of the memory bandwidth with other threads or processors. And so you might span some of your threads across NUMA regions for higher throughput, or you might try to focus some of it to only run these threads on specific NUMA regions to give to give more bandwidth, for example. And then there's things like memory locality as well. If you want to use caches, or you don't want to use caches or memory from different NUMA nodes, as an example, and over subscription or underutilization, you don't want to run multiple threads per core. So what MAP gives us kind of visualization and to make sure that some of these things like resource balancing, memory locality, or oversubscription, under subscriptions aren't issues. And it gives some commentary as well. So if there are issues, it will give you some errors to say that you're spanning over NUMA regions or you're oversubscribed to some cores. And then from this commentary, you can do some changing of your srun command, for example, to improve that. Okay, yeah, so that's everything from slides. So the last thing is to kind of look at some of the hands-on. Does anyone have any questions before I move on to the hands-on? Okay, yeah, so this is looking at optimizing the matrix multiplication. And I mean, if you want to get some more information, this is work example here, and it gives you kind of more. Sorry, is there a question? It gives some more information about those examples. But you can follow these steps just to build this application. So to do this, the first, this is a Python application, so you have to load Python, and the Python module on Perlmutter, it should have everything packaged up with it. So NumPy and MPI for Py, those type of libraries. Then we can do is make this example. That should build, which it has. So there's two things you could do. You could either run. So the other thing we need to do is we need to export. So this for its training folder. So there's two things you could do. You can either just run it through this batch script, getting rid of this bit. This is running it through a job submission script, and it's getting the reservation, and then if you just run map minus profile and then this srun command, what will happen is it will run the application and connect samples with it. Yeah, so that's running. It's going to take quite a lot of time to run because it's not a very efficient application. But if you want to start collecting some hardware counters, where we can run, and this is all in the hands-on slides. We can do map minus list target hosts. Yeah, so because I've already installed this, I don't need to install it again, but you might have map asking you if you want to do a forwards probe minus install equals user. So if you run that command, then it should install the forwards probe. And then from that, what you can do is you can see which hardware counters are available, which you can start tracking. Okay, so these are the things that we can track, and once we select which counters we want, then this will be available in map. So the ones that I'm quite interested in is this cache misses, only because this matrix multiplication example isn't very efficient for the cache usage. So hopefully this is not going to take too long to finish. But while that is busy running, what you can do in map is, so this is ready and the profile is being created. We click on Linaro map in the GUI, and what we can do is we can load some of the you can load a profile data file. So this will load the data file that's been generated on Perlmutter to view that the profile. Okay, yeah, so that finished. And this, so because that finished, it created this map file, and then what we can do is we can just view this map file. So this run for
And
47.
we can see your screen, or maybe it's just me. I can just see your terminal.
Oh, is that okay? So
Yeah,
that's it.
yeah.
Yeah, so
Yep.
I pressed something and it made it disappear. Okay, you can see that the map profile, right?
Yes.
Okay. So this is the profile here, and what I'll do is if you click on help and then the user guide, should open up the user guide here. And then we can, from this user guide, we can go into map and metrics view. And from the metrics view, we can look at things like the CPU instructions. Okay. Just while we talk through this map file, I'm just going to run another job very quickly, just so that it's running in the background. Um, because we've installed the Forge Pro, what we can do is we can start tracking some of the hardware counters. The way you do that is when we listed everything, we saw that there were cache misses we can start tracking. So we can start tracking some of the cache misses for from the hardware, from the Linux perf sets of counters to track. We'll have to put target host equals this authentic and just run this example. I'll just run that in the background while we look at this map file. Okay. So what we can do is we can look at metrics and then we can look at the CPU instructions here. So this application ran for 37.5 seconds. And if we look at this main thread stacks, we can see that most of the time has been spent in main. And from main, 66.0% of the time is being spent on the cmalt lib malt. So on this line over here. And we can change this by clicking this clock. And we can see about 3.3 minutes in terms of core time is being spent there. So that's quite a lot. And kind of map is really focusing on we want to investigate what is going on over here. So we can zoom into this as well. And we can see from just the zoom here, all of this time is being spent on this cmalt lib function. And from here, we can see what the CPU floating points are. So this is 99.5. And if you look at the user guide, yeah, so the hint that the user guide is saying for this one is that the high values here suggest CPU bound areas of the code that are functioning as expected. It's kind of saying, yeah, this is fine. We kind of expect the CPU floating point to be high, the CPU integer Yeah, so this is, we kind of expecting the CPU integer to be high, but this is quite low in this area. And then the CPU memory accesses as well. It says typical cache problems include cache misses. If anything is 98% and above. So high values here may indicate inefficient structured code, extreme high values, or cache problems. You can say, well, this does seem quite high. Maybe we should be looking at what the cache is doing in this area. So hopefully the next run is finished. Which we've collected some of the cache information. So let's see if we can load that one. Something. That's interesting. I think I put an intentional bug. Okay, yeah, come on find. That's interesting. So it finished running, but didn't create the map file. I'm not sure what happened there, but if you run that command, it should give you some cache miss information. I'm not sure what's happened there. Maybe I'm not sure what happened there. It's bizarre. Could be these things as well. Let me just try this. Yeah, I think it's these quote marks that caused the problem. It didn't like the copying from the slides with these quote marks. I think that might be the problem. Let's just retry that.
So we don't have this flag in this slide, right? The flag that we have.
No, but if you do this one, map minus perf metric list,
Let me just cut here.
yeah, I think yeah, perf metrics equals list. It gives you a list of all the different perf metrics that you can do it. I've just copied this one. So if you copy branch misses, you do minus perf metrics equals cache misses, and then minus target host equals this authentic AMD, which is the Forge probe that gets installed when you run the install equals user, which is in the slides. Right, okay. Yeah, so anyways, we need to look at this CPU memory accesses. I'm trying to get the cache miss information. Hopefully that will come in the next run. But this is really where we should be focusing at the time. And it's nice as well, you can kind of look at this report and export a performance report. Oh, sorry, not that one. So view HTML in a browser. And so this is just a performance report. So if you don't really want to get into the math file, you just want to kind of get an overview of performance. You can see here that we're spending 0.4 seconds in the Python interpreter, spending most of the time in compute, and MPI is quite low, and this is quite low. So the things that we should be focusing on is the compute, and most of this compute is being spent on this line here, and we're saying this line here is at least what the docs is saying is that the cache is quite bad. So what we're trying to do is we're trying to collect some cache information to confirm that. Yeah, and even what this performance report is saying is that the memory accesses is quite high. Yes, significant time is being spent in memory accesses, and we really want to kind of look at the cache performance there. Yeah, so this is what performance report is kind of guiding us to look at the cache as well. There we go. Okay, so that's a bit better. Yeah, I think it was this quote marks just copying pasting from the slides that caused the initial problem. Low profile data. And because we've now collected them, we should be able to see Linux perf events. And we can see, yeah, that the cache misses, yeah, 102 missed events per second, which is very high. So what's occurring here is there's just a lot of cache misses in this ml.py, in this mltlib.mlt function. What we can do is we can have a look at that performance, and then we can see what this is actually doing. lib.c. And all it's busy doing is this matrix multiplication, and it's got ij and k. And this for loops and calculation is making very inefficient use of the cache. But fortunately, in this this worked example, it gives us a fix. So instead of it being this, we can replace it with this. Okay, then we can make this again. There we go. Now we've changed the line of code to make better use of the cache. And we can see what map is busy telling us now, and kind of did we improve it or not. Okay, so that's busy running. And while that is busy loading, we can look at just going back to the origin, sorry, the profile with the cache misses in. And there's a range of other things we can look at. So once we kind of solve this CPU time, we can look at things like MPI as well. And you can see we can sort of drill into that and see where the time is being spent for MPI. So this bit here is spending it on year. So this com receive, and then this bit here this should be, well, we can look at the functions actually. Yeah, so all this time is being spent on this MPI finalize over there at the end. There's actually quite a long wait there for the finalize, which probably shows that there is a bit of an imbalance here, which makes a lot of sense actually, because only rank 0 is busy doing all of these calculations. So there's a lot of setup here. Rank 0 is the only one doing anything, and then everything else is busy waiting for it to finish. So that's kind of like an issue with the way that this program is written. It'll probably take quite a while to make this a little bit more efficient. But this is just a way you can see kind of what the MPI is busy doing as well. There we go. Okay, so this one finished, and this should be with more efficient cache. Because the runtime has gone down to 20 seconds. So there's a bit of an improvement. Yeah, so we've actually reduced this quite a lot. And if you look at the cache misses as well, links perf events, yeah, so we're now at 18.1 missed events per second. So actually this has improved a huge amount. The cache misses has gone down quite a lot. Yeah. And we've got quite a good, it's 13.3 seconds. So we've gone down from, so if we do reports, and we can view the HTML report in the browser. And we can see that the original one, we were running at 38 seconds. And by making that change, by making more efficient use of the cache, we've gone down to 14 seconds, which is a really big improvement. And the cache misses is 3.32 misses per second. And we can see we've gone from a very high compute to a very low compute. So the next thing that we need to work on is this MPI, and we need to kind of work on why this MPI wait is so long on this end over there. Yeah, but that's an issue with how this code is written, and that's not a very easy thing to fix, and this will probably take quite a while to actually fix it. But it's just nice that map is able to say, or performance report is able to say what we should focus on, and then using map to kind of drill down into why that is actually occurring. Okay, so looking at CPU instructions again. So one interesting thing is we have no CPU vector floating point operations, which means that there's no vectorization which is occurring. And this is quite easy, or should be quite easy to solve if we go back to the performance make file. we should just be able to do minus fast to give it this extra flag to make use of vectorization. So while that runs, another thing that I want to kind of look at is some of the GPU profiling. So if we look at something like T-Leaf, I'm just they're running in the background, so I kind of want to move on to GPU stuff. We've got 15 minutes left, so I want to cover kind of GPU debugging and profiling in 15 minutes very quickly. So this is running T-Leaf, and what you can see here is the blue, which is MPI, and then there's this purple here, which is waiting time spending waiting for the accelerator. And we can look at the metrics here. If we look at the NVIDIA presets, and what we can see is the GPU utilization is quite low, really. So what this is saying is not really making that much use of the GPU. I mean, you can also look at things like the GPU memory transfer rates, or how much data is being sent from the host to the device. And we can kind of zoom into this and look at where these are busy occurring. Yeah, so you can see that we have two GPU kernels that are running, and they're spending this much time in each one of those. Yeah, so this is just how you can look at some of the GPU code and kind of seeing if the GPU is being utilized well, and kind of what the memory transfer rates are between device to host, and off-device memory transfers as well, to see if that's being or the data is transferring as efficiently as possible. So yeah, so that's finished running. So we go back to the matrix multiplication example and load the profile data. And now we can look at metrics, and we can look at CPU instructions. And we can see now we have some CPU floating point vector as well. And this time is reduced down to 12 seconds. So again, if we put this into a performance report just to compare everything against each other, we had 14 seconds and now we had 13. So that vectorization has, you can see a vector numeric operation has slightly improved it, not that much, but the cache misses has reduced as well. So we get better cache utilization, and we reduced it slightly. Okay, is there any questions around profiling? This is kind of how you'd use the profile, and kind of going through the process of, this is the improvements I made, using performance reports to get some hints and tips, and then looking at the areas where the bottlenecks where this where the performance issues might be occurring, and then trying to think of ways to fix that. But if there's not any questions, I can just spend the next 5 minutes very quickly just looking at GPU debugging. Okay, it's like silence is golden, so I'll just quickly move on to GPU debugging. Hopefully it works. So I'm going to do an interactive session. I hope that this will work to get a GPU allocation. And again, all of this is in the actual slides. Okay. We're going back to correctness and then GPU NVIDIA melt. You should just be able to run make in this directory. And that should build these examples. And then what you can do is you can do DDT minus connect by just running this matrix multiplication example. Yeah, so DDT automatically auto detected the GPU, so that should just run. There we go. So if we run this, what should that's interesting. So when it hits one of these GPU kernels, the debugger should halt. But I think I know what the issue is. Yeah. Yeah. Okay. You can enable this or disable it. So stop on CUDA kernel launch. If this is enabled, then every time it hits the kernel, it will halt the debugger, which it has now. Okay. So if we look at the kernel, actually, yeah, if you look at the stacks will be quite a good place to look. So if we look at this line here, we can see that there's loads of GPU threads on this line on matrixmul.cu58, and then there's a range of other ones on another line. What we can do is we can use this kernel progress view to kind of look at the threads we want to control. So for example, if we click on this one, which is block 15.1, thread 19, 15, and if we step that, then we're only stepping those 32 threads. If we're going back to the stacks, we can see that this is the one that we controlled, and it gives you that indexing system as well. But as I said, that if you set a breakpoint over here and we run that, then all of the threads will run. So you can't just run those 32 threads, everything is going to run. And then from here, what you can do is, I can find it. There we go. You can play around with this calculation. So you can add expression of it, and we can just calculate what the value of this part of the calculation is, and we can calculate what the value of this part of the calculation is by using expressions. And then we can also calculate what C sub is as well. And then as we run this, you can see all of these. You can see how this evaluation is updating the value of C sub. So you can kind of look at this and see if it's calculating this correctly. And again, with the GPU kernels, you can look for each one of these as well. So all of these threads and what their value is, and if they're calculating this correctly. If we remove this breakpoint and we continue to run, then the next kernel will hit and the GPU progress. So actually, this is not utilizing the whole GPU. Yeah. But again, with this, all the trace points should work just as normal CPU code as well. All the trace points should work. You should be able to see all the local variables and yeah, all the stack views, and the GPU device as well tells you what you're connected to. Yeah. Okay, I'm conscious that we got like 5 minutes left, so I can spend that time asking any questions. I mean, is there anything? Oh yeah, sorry. I hear there's a hand up.
Yeah. How do you switch to a particular thread in a particular block?
Yeah, so if you do use the kernel progress view, you can see some of these as finished. I'll move on to here. So this is a specific thread in a specific block by selecting this. You can see over here which block and thread you are, because this works on the block thread indexing system. And you're selected here. But only the ones in green are the ones that are still active. Everything in white means that, you know, either the kernel has finished or it's not run yet, or the threads on the kernel has finished.
And those, I forgot the name for those charts, like with the small charts with the variables with the white and the black line in the middle. So
Oh,
are
yeah.
those like a block wide or like a warp wide? What's the locality there?
I don't think that Sparkline. Oh no, Sparklines do work. Yeah, I
Yeah.
think these are block. These are based on the block, I think.
Okay.
I need to double check actually, but I think they are block based.
Thank you.
Great. Is there any more questions? I know we covered quite a lot. Okay, here's another question.
Yeah, hi. I have a question. Maybe you've covered it and I missed it, but suppose I'm interested in this profiling, getting in the performance reviews, and basically, what if I'm trying to run it on Python with API for Py? I was wondering if I need this like extra compiling step beforehand, or can I just run my application like MPI exec, for example, then just write perf report tag in front when I launch it, or do I need this extra step beforehand to produce the reports?
Typically, you wouldn't need an extra step, but I'm not entirely sure if there's anything on Perlmutter that is a bit different. But usually, you wouldn't need to. It should just compile and run.
Yeah, so in principle, there's just compared to like how I normally would run, I would just add this extra perf report, or for example with map profile, and then run as I would.
Yes, there shouldn't be any extra steps.
Okay, all right, thank you.
Let me just check. I'm sure that the application I used, performance, and then there was mimult.py. Yeah, so this is using MPI for Pi, the application that we were running just now. And if we look at scripts and then submit job.sh. So what you do is you'd run this command if you're running that Python script just normally. And what we're doing is we're just running map minus profile. You ignore all of the perf metrics. If you ignore this, all we're doing is map minus profile, and it just works.
I see. Okay, and maybe another question. So does it matter if I write srun or MPI run or MPI exec? Would they all work, or does it have to be srun in particular? Does it matter?
Yeah, you have to use srun. And
I have to.
Yeah. By the way, that we have a Makefile here. This is to build the C code into the shared library that Python can use. But yeah, if you don't have that kind of thing, probably you can use it on your Python code.
I'm sorry, on what code? Sorry.
I mean, we do have a Makefile here, but that is to build the C code. You know, the Python using the C code. So
right.
we build the C code and make it as a shared library so that the Python code can use it. So that's why we have a Makefile here. So.
But it's not like a requirement for the performance. It's just for this example. Yeah. Okay.
I mean, this particular example uses this C interface and the Kotlin interfaces.
I see. Okay, thank you. And then for MPI for Pi, for example, I know there are like different MPI implementations, like MPI CH or open. I think it's Open MPI or something like that. Does it matter? With like a standard MPI implementations, it would work.
Yeah, I have no idea, but
okay.
Yeah.
All right. Yeah. Thank you. Thank you for your answers.
Yeah, you use MPI SDH. I didn't understand your question. Yes, we built the MPI for Pi using the Cray and Pitch.
Okay. Thanks.
Okay. Is there any more questions?
So I have one question. So profiling on GPU, I mean, how does that sampling work? I mean, you said that we have 1,000 samples per MPI rank. So how that translate when you collect the data from GPU?
Yeah, so for GPU, we use the CUPT interface.
Okay.
And what we do is we sample that at particular intervals. And then we slow down the sampling the longer the program runs for. So the scalability is in our sampler, but we just use the CUPT interface to grab all the information. Okay. And that will have its own mechanism of how it collects that information. Great. Yeah, I think we are at time anyway, so I think we just finished just on time, which is good.
Yeah. Are there any other questions? Well, then, yeah. So then let's finish our tutorial here. But please, keep in mind that to participate in the survey, and that will help us to improve our training here. And thank you very much for Rudy. Thank you very much, Rudy.
Yeah, no worries.
These are great materials. So yeah, thank you.
Okay, yeah, thanks a lot. See ya.